thank you for allowing me to be here. I appreciate it, visiting from the U.S. I'm just going to make a comment later this afternoon when we do the PDF JADE, but mostly PDF demo, as Bert said. We'll be going through it, and it might be that we don't get to do everything here, but you will have access to the database in JADE for a couple of weeks after the meeting, and it is via a web link. So somewhere in your information will be the web link. You should have a username, password, and it's good for a couple of weeks to try it out, okay? All right, so thank you. So I'm going to use this morning's lecture, and the information is uploaded to the lecture information here from the presentation. A bit about the powder diffraction file and a little bit about the JADE software. But the powder diffraction file, so the interesting is that we refer to it as the PDF, and then there's this company called Adobe that has something called PDF. And then there's this PDF pair distribution function. So we are the PDF powder diffraction file, okay? All right. So just a little bit for your information, my background. Previously, I was at the Eastman Kodak Company working in the research laboratories in Rochester, New York. That's upstate New York. Currently, I'm at ICDD, where I'm the executive director, principal scientist. And this is what I did when I was at the Eastman Kodak Company. We worked in a research laboratory, but it was an industrial research laboratory. And so our role was to look at new materials, but also to solve problems. Something would come into the laboratory, and we heard the excellent presentation just a few minutes ago about identifying phases. What's there? And even if you could identify the phase, why did it not work? So getting into microstructure analysis. So this is what the involvement and where I gained my primary experience in X-ray diffraction, X-ray crystallography. So how did the powder diffraction file get started? Well, we go way back. We go back to Röntgen, who came up with what we would call the discovery of X-rays. At the time, he didn't know what to call it, but the term Röntgen rays was really the term used at that time in 1895. You'll see the picture here. This was his first published hand radiograph, actually the second one that he collected. And you'll notice that there's a large item right on one of the fingers there. This is a ring, okay? And this is a picture of his wife's hand. He didn't know what he was working with, but he did know he wasn't going to put his hand in the beam, so he asked his wife to volunteer. In 1912, we had, this is the first Lowy pattern. And you'll notice that it doesn't look too good because in the original experiment with Lowy, Friedrich, and Knipping, they actually had the crystal 90 degrees to the detector rather than right in line with the crystal there. So they had to do a few experiments to get the geometry fixed, but this was the discovery diffraction. The nice thing here is that Lowy and the graduate students were Friedrich and Knipping. The graduate students did the work. Lowy, the professor, got the Nobel Prize. This is the normal procedure at the university, right? And then we have Moseley. And Moseley's credited with the concept of X-ray fluorescence. And really, at the point, they were calling it X-ray emission. And he was able to determine that depending upon the element that you had characteristic radiation. And you could use that characteristic radiation to identify elements in a particular sample. This is the early Bragg diffractometer from 1913, the father and son team, the Braggs. And at the time, you were working with single crystals. Now, they figured out how to do crystal structure, but they were still working with large single crystals. And what they would do is they would move the crystal. They would move a detector. The detector was a gas-filled detector. And then they would look at certain crystal faces and try to elucidate what was going on from a structure point of view. So for many years, this was what crystallography was, working with large crystals. And the belief was that if you ground up the crystal, you would destroy the crystallinity. In 1916 and 1917, simultaneously, Dubai and Scher in the U.S. and Hull in the United States were working on the concept of powder diffraction. And they were able to show that you could grind up a crystal, or you could even look at a solid material that was crystalline, but not a single crystal, and you would get these powder rings where each little grain was contributing to that ring. And so this was really the start of the powder diffraction technique. The detector was a photographic plate. But what Hull also added to the technique was that he showed if you took two different phases and mixed them together, you didn't get a new diffraction pattern. You had an overlap of the two patterns. And so this was the first, we call it the discovery of phase identification by powder techniques. A Dow Chemical Company took it to the industrial scale. This is from 1934, and they had X-ray source with multiple X-ray film cassettes surrounding the source. They could put 2 samples in per cassette, so 12 cassettes, 2 samples, so 24 samples of data they were collecting at a time. And the result was the start of a large powder diffraction file. So in 1938, they published a paper, and the paper was chemical analysis by X-ray diffraction. And 2 key components came out of this. One, they published close to 1,000 diffraction patterns in this paper as reference information. And the second thing was the technique on how to use that data to try to identify phases. So the image on the left here, that is the original Hanawalt manual. It is at ICDD. We like to jokingly say that you could see some of the entries will have a line drawn through it. This is when they figured out that they didn't have the right analysis of the material. And we like to refer to that as the original delete key in terms of technology. But the publication then, they took that information, and in 1941, ASTM, American Society of Testing Materials, published that data on a series of cards. And these cards were sort of 3-inch by 5-inch index cards. And so the powder diffraction file and the cards that people refer to started with this particular data set. You buy basically a case of cards, you'd put it in some kind of a shelf, and conveniently one of your colleagues would pull that card out to take a look at it and not put it back in the same place, and then you could never find it again, okay? So with time, the cards became books, and the books became digital matter. And so we've made that transition where today everything is electronic digital format. So we refer to the specific entries as PDF entries, but many people, and even we'll put the information in our database, we'll call them cards to this day. All right? So what is the database? Well, the premier database is PDF5 Plus. It has 1.1 million entries in the data, and ICDD has a partnership with a lot of the key databases. So we have data that's been collected by ICDD over the years. We have data from the FIS ICSD database. We have data from the CCDC, Cambridge Structure Database, the LPF database, and a little bit of NIST data. Now, you'll notice, for example, in the CCDC data, they have also themselves over 1 million entries in the CSD. We do not put all of those entries in the powder diffraction file. Our focus is the phase identification, quantitative analysis, so phases that you might find in terms of your analytical work. If you want to do modeling work with organics, you'll want the full CSD from CCDC. Okay, when you open up the database, you have what we call our search form. Back in the day, it was the Hanawalt manual, but you had the search form, and the search form allows you to do more than just say, can I search for a particular powder diffraction entry or a powder diffraction card? And there are several components here with this of what and how you can do your searches. And I want to emphasize for a moment the one called quality mark. Every entry in the powder diffraction file goes through an editorial review, and it's assigned a quality mark based on our editorial assessment on the quality of the data. Remember, we have data that ICDD has been involved with the collection, but we also are working with data collected by scientists around the world. And not everyone does the same data collection, not everyone has the same data quality. So we do the evaluation, we assign the quality mark, so you get a sense about how good are the data. So the top data are star and good data from polymer type materials. They're given a green, kind of like the traffic light. Green means go, okay? The yellow means okay, good, but just understand there'll be a comment why it didn't get the green quality mark. And then there's red, which means it's the lowest quality. Now, why would you put lowest quality in the database? Sometimes it's the only data available. Someone has published a pattern, but there's some delta 2 theta errors that we see. We'll make note of that to say, understand, here's this particular entry, but also be careful when you're comparing it to your data. So an example, why does data curation matter? Here was a pattern. It was a publication, and in the publication, they said that this was a pattern of sodium alginate. The sodium alginate is a sodium salt of a biopolymer, and you typically don't expect to see these really sharp peaks as part of this type of a pattern, okay? We have a study going on at ICDD looking at polymer materials, and we've collected a pattern of sodium alginate, and so the blue pattern you see here is in fact just that. So why do you see these sharp peaks in this published paper? Well, it turns out that we identified the phase, and it is a sodium sulfate. And you read through the paper, they had washed the material with some dilute sulfuric acid. It basically precipitated out with the sodium from the sodium salt of this biopolymer, and therefore you got an overlap of some sodium alginate is there, some alginic acid is there, but there is a lot of the sodium sulfate. So this is what data curation does, to look and see, does this make sense for a particular PDF entry? Okay, so suppose you're looking at a paper. This particular paper, one of the authors goes by the name of Rosanna Rizzi. I don't know, does anybody know a Rosanna Rizzi here? Okay. And as you're looking at the paper, it talks about tricalcium phosphates with a variety of rare earth materials in terms of some studies that they've done here. And you can do a search in the database and say, well, I want to do a search that, for example, that says I have to have calcium, phosphorus, and oxygen, and I might have certain rare earths, and the author is Rizzi. When you do that, you get a number of hits, a number of entries in the database that show these data have in fact been put in the powder diffraction file. And you can open up that particular PDF entry, and with that entry, there's a lot of information besides just the despacings, intensities for phase identification. One of the things is that the database is flexible for what wavelength are you working with. We heard presentation before mine that we look at things in terms of despacings rather than 2 thetas, because you don't know what radiation someone's going to be working with, or maybe they're at the synchrotron, maybe they're doing neutron work. So you have the flexibility to change the wavelength that you're working with. So you can be working with laboratory X-ray data, you can be working with synchrotron data, we can even do constant wavelength or time of flight neutron data, as well as when you have the atomic coordinates, you can simulate the electron diffraction pattern as well. So the flexibility is there of not just standard copper K-alpha X-ray source lab radiation. Multiple sources are available to be used. So when you open up the PDF entry, again, the information that's there is beyond just the despacings and intensities. When the raw data has been provided to ICDD, we're including the raw data in the database, so you can actually see how does your pattern compare to the one that the author collected. Every pattern can have a simulated profile, and we'll go through that in the workshop later this afternoon. But with the simulated profile, you can assign a profile shape to it, even work with crystallite size effects to see what does that do to your powder pattern. With the structure, those phases that have the crystal structure, you can look at the 3D structure. You can look at basically the polyhedra H function of it there. You can look at the bond distribution, and you can look at the selected area, backscatter, diffraction patterns, ring patterns, and ring, whether you're using a full 2D detector or even a strip detector, you can simulate the powder pattern. We have extensions on the selected area, electron diffraction and the backscatter diffraction. And this is actually quite helpful, particularly as an extra tool when you want to try to do some identification or even structure work using electron diffraction techniques. Here's linagliptin. We actually did the crystal structure in conjunction with another group. Surprisingly, it's a very popular medication for cholesterol treatment, and yet no one had actually succeeded in getting the crystal structure. So by combining synchrotron work along with electron diffraction work and using our extensions, we were able to get the crystal structure. And it turns out it's a hemihydrate, hemiethanolate as well. A little solvent is in the lattice. You have the ability to do enhanced 2D XRD analysis. We can look at the 2D detector spectra, and as mentioned earlier, you can also look at strip detector spectra. You can compare these data to entries into the database. You can integrate the 2D data, and with that, you can do your phase identification. And then with this, you can overlay any of the PDF entries and confirm phase identification of single-phase or multi-phase samples. We've now added, it's been about a year now, we're adding Raman data to the powder diffraction file. Why? It turns out, particularly in minerals, Raman is very popular to help do identification of mineral materials in the laboratory, micro Raman. In the mining industry itself, handheld Ramans are very often used to look at a vein that's running through a particular mine area and what is that material. And so now we're adding the Raman data. This year we'll now have about 900 entries into the database. We have a special grant and aid associated with that. We're working also with Bob Downs with the Russ group as part of this program. So we'll see more and more entries. We'll start adding different classes of materials as well. But again, the idea is to help correlate the analysis of materials. Just a little bit about JADE software. So this is for phase identification. So through the next 2 or 3 days, you're going to hear different software. You're going to have different diffractometer companies have their software, and they all make good software. It's good stuff. Everyone has their little flavor, how they do things a little different. And so area we do happen to have our JADE. JADE is designed, it was designed primarily for phase ID and quantitative analysis. It is flexible in terms of the file formats you can read. It can read ASCII, binary, GSAS, CIF, XYE, but also can work with all the diffractometer companies' data, and we make custom as well. Someone contacts us and says, I have a custom format. We just finished cleaning up one for ESRF because they have their data, I'll call it metadata, is in a separate file compared to the raw data, and so we can work with that. So the idea, though, is to be able to do phase identification, quantitative analysis, but we also have something called the toolkit, and the toolkit allows you to do a number of specialty analyses, and if time permits, we'll talk a bit about cluster analysis, okay? Now, I want to emphasize a couple of points about phase identification. We had an excellent talk prior to mine, and we had some comments there. Earlier, Paolo Scardi made some comments, and I want to emphasize a few points here. Three things that we see consistently that hinder phase identification: sample transparency, sample displacement, and counting statistics. Sample transparency, you get your sample holder, particularly in Bragg-Brentano mode. You pack it full of a low Z material, an organic. The X-ray beam is going to penetrate deep into the sample. And I think if we can see in the sort of the diffraction pattern here on the left, you'll see the black pattern is a sample holder that is filled with an organic material. It's a pharmaceutical. The red pattern is the same material sprinkled on a silicon zero background plate. So two things will happen. You will lose resolution and you will get a shift to lower angle when you have transparency. Now, these are normalized intensities because when you sprinkle, you'll lose intensity. So you'll gain resolution, you'll be in the correct sample position. Sample position is very important for phase ID. I think we heard earlier the comment that Bragg-Brentano has its bigger problems at low 2 theta. Transparency is the issue, okay? Sample displacement, this is probably the most common error that we see, where people will put their sample in some type of a sample holder and they either put too much sample or too little sample there. And if you have that sample displaced, you're going to shift your peak position, okay? And again, phase ID is peak position. And if you're moving that around, you have potential for an error. And then finally, we heard a comment earlier about counting statistics. And the issue at hand, of course, is that when you have low intensity peaks, can you really differentiate those between what's in your noise? And so you need to count enough counts to be able to, in fact, get good counting statistics. All right. Other things, preferred orientation. So with preferred orientation, here's a sample. It's the lepidolite. This is a lithium-containing mica. It's a very hot mineral right now, hot because it has lithium, and everyone wants to get lithium. How do you get the lithium and extract it? If you take the material as received, it's a platy mica-like material. And if you want to randomize the pattern, if you grind it for 3 minutes, all you've made is just smaller little plates. They still orient when you pack it in that sample, okay? If you do extreme milling, 23 minutes, well, you start to randomize the sample. The problem can be when you mill a material for 23 minutes, you do other things to the sample. You introduce, defects into the sample. You might even change the polymorph of the sample. So you have to find a balance. Preferred orientation can be problematic when you're trying to identify phases. The other thing you have to pay attention to is sampling statistics. We heard a little bit about, how many particles are you looking at and how many of them are oriented in the right orientation to get data. So this is a sample of they're rutile TiO2 needles. They're gold-looking needles grown on quartz. And if you take a few of those needles, lay them on a flat sample holder for Bragg-Brentano diffraction, you get the diffraction pattern on the left. If you try to do phase ID, you'll never get the identification. On the other, and the reason is because it's random particle statistics. It's not even preferred orientation. It's just random statistics. If you grind it up and make a powder out of the material, you get a very nice pattern for rutile TiO2. So sample preparation as well as your data collection are critical. Now, the other thing you want to pay attention to when you're doing phase identification is you're going to get some kind of result. I think we heard the term, the last presentation, some kind of figure of merit. And different vendors use a different value, and that's okay. Just know what they're doing so you know what it means for your result. In the ICDD sieve, out of PDF5+, we use something called goodness of match. You take 8 peaks, and if you have a perfect match for intensity and position of 8 peaks, you get 1,000 points for each match. Perfect score would be 8,000. Very unlikely you're going to see 8,000 in a pattern. We have another software program, figure of merit, that the smaller the number, the better your match. And then we have another program, figure of merit. The higher your number, the better your match. So this is all okay. You just need to understand what your particular program is doing. Now, the other thing you'll see in all of these is they have something called an error window. What's that mean? Well, we talked about that sample displacement. We talked about that transparency. You're going to have some kind of an error window that says plus or minus on my particular peak position to see if I can get a match. Now, if you make that number really small, thinking that you really got good data, you also are restricting the number of hits that you might see when you do your search match. If you make that number too big, you'll get too many hits. And so you want to be careful. The best thing to do is collect good data, okay? But if you're not getting a match, you might want to open that error window a little bit. All right, phase identification. So this was a data set collected by our friends at Momentum Transfer. It's cement. NIST makes a cement clinker, and the intent is to see, can you identify the principal phases in the cement? And it's a difficult analysis, because in this region here that I have highlighted, there are several peaks that overlap each other. And this is a case where having synchrotron data really helps with the analysis, because you can resolve out some of these closely spaced peaks, okay? When you go to do the analysis, in fact, you can identify the principal phases. And the problem is, particularly for the A-light, B-light, and ferrite, they have peak overlap. And so being able to resolve out those peaks is an important part of the phase ID. In addition to that, the question is, can you say how much of each phase is there? Why is that important? Well, when you're making your cement, you need a certain composition for the cement to work, okay? And you don't want to be the person that's putting the road down where there's a bridge and you've got the wrong composition, okay? All right. Now, one of the things is that there are manual methods, like in our Civ, that you can sort of go step by step to do phase ID. And then you have computer search matches. We heard about the previous presentation, the program offered by the Barre group, where you have some kind of automated search match. You have the program called Match. You have Brooker's EVA. You have HighScore. So there are multiple programs out there. And the difference between the old Hanawalt we heard, and I emphasized the point that you heard in the last talk, it's really looking at the whole pattern. It's not just where are the peaks, but also where do you not have peaks as part of it, okay? So if we look at a particular pattern here, one of the things is that you look at, say, what does computer search match do for us? And here's a case where you say, identify the phases. So it's going through here, it's identified the phases, able to plug the data with the atomic coordinates into Rietveld refinement program, and able to do your Rietveld refinement and quantitative analysis. And even you have your information about the different structures of the phases present. And all this is accomplished in 30 seconds. Okay? Now, my question to this group, you have a new sample that comes into your laboratory, and you say, I'm going to do this one-click analysis. How many of you think you're going to get the right answer? Anyone? You're right. You probably won't. You can't do one of these, sort of hit a button, get an answer type test until you understand the system you're working with. You have to understand the system. So luckily, they still need people to do that. AI is out there, machine learning is out there, but when you're getting new systems, and particularly complex multi-phase systems, you still have to understand something about what's going on. Once it's well established, these kinds of techniques are very good for quality control. When someone says, we're making a certain material, we have certain phases there, and it must meet a certain specification, that's when these techniques really, really do work. Okay. Now, sometimes you don't have the powder pattern. Okay, sometimes you have a paper and someone has a structure, and you want to know, can I match that to something in the database? So here was a paper, and it was reported that some material that had been extracted from out in space and had been brought back to Earth, and they had the material to do the analysis on. This is one of those cases where they've got the apparatus and, they had to figure out for 6 months how to get it open and get the sample out, etc. Okay. But ultimately, the data were collected, and what was unusual was the claim that this material coming from the moon had water, okay, as part of the lattice. And so, there's a crystal structure that was performed, and then this was the reported structure type, okay? And when you have a crystal structure, you can get a CIF file. And with the CIF file, you can import that into a diffraction program. And in this case, we can take this, say this is what the structure looks like, and you can calculate a powder pattern from a crystal structure. So these are the things you can do in JADE. So if you have the database, tie that into JADE, tie it into any of your diffraction software, you can in fact confirm and identify the mineral type that was found, okay? And so even if you don't have the powder pattern, you can still go through the operation to see, is there something even isostructural that will tell you something about the powder pattern you expect from this material. All right, let's sort of look at a quick example here. Do a little downtime. Yeah. I'm not going to cut into lunch, okay? Promise. It's okay. We're working on an antimicrobial, and this antimicrobial was a silver copper oxide phase. Collected the powder pattern, a pretty standard powder pattern, and 3 phases were identified. Now, the phase that was desired was this silver copper oxide, but I have a significant amount of copper oxide and a little bit of silver metal. Now, this is where powder diffraction is doing more than just identifying phases. You're being asked to help identify and answer the problem. That's part of what you're going to do, all right? So you have structures. You can go into the database. You have PDF entries. There is a structure tab on the entry, and in that structure tab is the crystal structure data. You can import that data as a CIF file, and also by special request, we also can generate an STR file that will allow you to take the data directly into Topaz, okay? And from here, you can do things like read felt refinement. And when you do your read felt refinement on this material, you can in fact try to quantitate the amount of each phase that's present. And we see here that even though silver copper oxide was the phase we were looking for, the major phase is silver oxide. Now, the odd thing is also there's a little bit of silver metal. I mean, silver metal and silver oxide, you're going 2 different directions of oxidation reduction. So what did we learn, and how do we help answer the question? So it turns out, in this case, the production operator had incorrectly weighed out the amount of silver salt as part of the starting operation. That's why you had too much silver oxide. So that answered that part. But the second part was there was a finishing step in the production process, and that finishing step actually was starting to reduce some of the silver oxide to silver metal. So there are 2 problems we figured out, and part of the result from the XRD result was, number 1, put a new standard operating procedure in place so that you actually weighed out the right amounts of material that you were going to be working with, and change that last finishing step so you didn't do the oxidation, or the reduction of your oxide. So this is where the material science end of things, when you're talking about powder diffraction, to help solve problems. Okay. And the sort of proof is in the pudding. It's an antimicrobial. We see at the top here, this is E. coli without the antimicrobial. Here it is with this called our errant mixture. And yes, you're starting to kill some of the E. coli, but you're not very effective. Here, when you have a pure silver copper oxide, you have essentially killed all of the E. coli. And that's what you're looking for, is to get the final efficacy result. Okay, Just a couple things here about we're linking to the our LPF entries. They are linked to the materials data platform system, so that you are able to now start working on the idea of tying crystal structures into properties. I mean, that's really where the direction is with big data. It's not just I have a powder pattern or identified a phase, but where are we going in terms of structure properties, okay? And for example, lithium manganese silicate, a battery type material, you can look at all of the different structure types that exist. And if you want to focus on one specific composition, you can do that, and you can see that there are polymorphic forms of this material. You can look at all of the crystal structures that have been determined, particularly at high temperature, low temperature, room temperature, and from that derive your complete phase diagram. And beyond the phase diagram, in this case with this particular type ternary system, you start to work on things about observed versus theoretical calculated structure properties. And this is what people are doing now, trying to design new materials, taking the structure and start trying to say, how can I design new materials faster for certain properties that I'm looking for? I'll finish up with a couple of things here that are not powder diffraction file. Okay, we at ICDD, we do have a scholarship program. Do we have any grad students here? It's all right, don't be shy. It's okay. All right. We have a scholarship program. This year we have 7 scholarships, $2,500 each. And the scholarship is named after Ludo Fravel, one of the originators of the powder diffraction file. You can apply at our website, icdd.com, and you write a summary of your research work for grad students in high energy scattering. It could be diffraction, fluorescence, neutron, electron. Your professor, your advisor writes a letter of support, and then all of the people who've applied, it is reviewed. We do look for getting what we call Fravel regions. So we would like to see certainly someone represented from the Europe region. Our representative for Europe is here in the back, Robert Dennebeer. So he's certainly available for questions, and I'm here for a few days. So feel free to ask us about the Fravel Scholarship. And we do have some brochures out here outside as well. These are the 2025 winners. We, again, look for regions around the world. They don't have to all be from the U.S., but we like, if there's someone available from Europe, Africa, Asia, that's what we look for in terms of getting the award. And there'll be 7 scholarships this year. We also sponsor the Denver X-ray Conference, and the conference is both diffraction, fluorescence, special techniques. We have workshops, we have poster sessions, we have technical sessions. We do provide student support through the Snyder Award. So if this helps with travel to the meeting, so if by chance you are interested in attending, it'll be outside of Chicago next year. So fairly easy to get to from Europe. Feel free to think about applying for a Snyder Award. Okay. This is the ICDD group. We have our main group in Pennsylvania, just outside of Philadelphia. We have our software programming group in California. We have a representative in China and a representative in Italy. And so this is the group that makes all of this happen. And I'll just finish with my favorite slide of my grandkids, and like to say, busting geodes, and yes, crystals are fun. All right. So thank you.